All right, good morning, everyone. Let's get started today. If you're online, remember to turn on your cameras. And so I shared last night, I updated the GitHub repo. I sent an email asking for you all to get ready for today's class. So basically, let me just show you what I have here and kind of what I asked you all to do. So this is the main folder of the class main folder for me, right? So we have the different projects that we've been working with. I asked you to excuse me, to create a new folder inside of your class folder called 05 terrain, right? And then inside of that folder, I asked you to create a code, data, and output subfolders to move the data set that I shared with you last night into the data folder. So that is the elevation.csv. It should be in your data folder. I also asked you to move the partial code into your code folder. So that would be the 0224 terrain partial.qmd. You should have that in your code folder. And I also asked you to create the project. And again, just a reminder, the project icon should be at the same level as the code, data, and output folders. If the rproj icon or rproj file is inside of one of those folders, it's in the wrong place. It should be at this level. You should be seeing something similar to mine. Okay, so if you have done this and you're ready to get started, just go ahead and launch that 05terrain.rproj project. So it launches an RStudio window for us. So if it launches for you, you're not seeing anything like you're not seeing a script as it is in my case as well. Again, you can come on the Files tab. If you're not seeing the main folder of the project, you can click on that R blue button to take you there. And then you navigate inside of the code folder and then launch the 0224 terrain partial QMD. All right. Okay, so just a refresher, we basically finished processing the EO data, right? So the EO monitor data, this is a very common layer that producers may have that you work with. So I'm glad that we got through that and we understood, the different parts that needed to be performed before that data is actually usable. So now you can think of it as we know how EO is performing in that field, how variable it is, what parts of the field are more variable than others, and also the EO levels, high, medium, low. So now the goal is that we try to understand why that is. What is causing those yield differences and also the yield variability across years that we saw on that data. So now we're going to start bringing different pieces of layers that is also common for producers to have. And the first one is going to be elevation. That's what we're going to be doing today. The next one that we're going to be bringing is soil electroconductivity data that we're going to talk more about it when we get to that exercise, but is also a somewhat common layer for producers to have that give us an idea of spatial variability and soil properties, especially related to texture for a field. So coming back to today's class, we have this elevation.csv file that has elevation data for this field. And we're going to be interpolating that data and also creating different secondary variables that we can extract based on elevation. That's our goal today, just to characterize the topography or the terrain properties of this field. And then in the future, we're going to use that information to try to see if that is helping us to explain EO differences. Perhaps, there is some parts of the field have a higher slope, water moves differently, maybe nutrients are also moving differently depending on where in the field, if they move with water. So all those things are important for us to be able to characterize spatial variability of yield in the field.
So we assume like the field is not leveled.
That could be, right? I guess we're going to see that today. Yeah, I guess when we get to the end of today's exercise, we'll be able to answer that question if the field is leveled or not. Yep. Okay, so our objectives for today, and even if we don't finish today, for this exercise here, are to first import vector layer of elevation. In fact, now that I'm reading this, I just want to say that we're not going to be importing a point vector layer. It's going to be a CSV. And then we'll turn that into a point vector layer. I just want to say that to not make it confusing given our previous conversations. Then we're going to interpolate that elevation data and then use that interpolated elevation data to calculate secondary terrain variables like slope, aspect, and flow direction that all depend on elevation. And then we're going to combine these different pieces of terrain variables into one object and export that to file so we can then bring it back in the future and use to relate to yield in a future exercise. Okay, so I left you here all the packages that we're going to be using. As you know, if you can go ahead and hit play on that chunk. If for some reason the chunk stops at a certain point saying you don't have a given package, you already know how to go ahead and get installed. I believe so. The one that we're using new today that we have not used yet is that I think we haven't used yet is Terra. I believe this was one of the packages I asked you to install in the first, like getting ready for class, the first script that I share with you. So you should have it installed, but if you don't, you can always just use the install.packages function and have it installed if that's the case. Okay, so today, here and there, I sometimes like to bring in some slightly different things just to expose you to some different concepts. In this case here today, if you recall, and we had an exercise about this, is we had multiple themes when we're using ggplot that we can choose from to make our plots look different. I'm basically, one of those themes is called theme map. So if you remember, theme map basically removes the X and Y axis like numbers and it makes it very clean for a map purpose. So I'm basically starting with theme map. I left you all the code. I don't have to really do much, but I'm just walking you through this. I've started with theme map, and then I wanted to do some further fine tuning of the options of theme map to make it look the way I wanted. So then I added a theme function after theme map and changed a few things here. So changing legend position to the right of the map, changing the panel background, fill, the plot background, legend title, legend text size. I'm not going to go through these very detailed, but I just want to say that everything you see in a ggplot, every single thing you see there, it's editable if you want to edit it. And the way that you would edit specific things would be inside a theme function. So here is just, I'm changing a few of them. And if I were to add a comma and hit, or maybe not, let me do that here and just hit tab here, these are all the things I can change. So it's like a lot of things you can change. So I just wanted to make that point. We're not really going to explore this as much ourselves. I just want to tell you that I started with theme map. I made some modifications that I wanted, and then I'm saving these to an object called mytheme_map. And then every time we go on a ggplot, I can just call this object mytheme_map, and it's going to apply all these, fine-tuning aesthetics to our plots. So just make sure you go ahead and run this chunk so you have that mytheme map on your environment, because we're going to be using that. Okay, so if you go to the next chunk here, the first thing that we're going to be doing is, of course, importing this data set, this elevation data set. If you recall, so let me just come back here and show it. I just mentioned that, but if you recall, this is a CSV. So you don't have the terrain V yet. You just have the elevation.csv. So it is a CSV. What function do we use to import it?
Read
Yes.
CSV.
Yes, thanks everyone. That's exactly right. So this is not an SF object yet, right? It is a CSV because that's how it is in our file system. So we use a read_CSV function to bring that in. So as you know, we're just going to do the quotation marks, get outside of the code folder, hit tab, get inside data, hit tab again, and select elevations.csv. So if you bring in, it just gives you some extra text there, but it's not an error. But if you're able to print it, so here's what we have. We have, so this is a data set that has, you know, about 55,000 rows, right? Where, and we have a handful of columns here. Let's just go through them one by one. So object ID and point ID are basically just an, you know, the ID of that specific elevation point. I don't, you know, this data set here, I don't really know how, like, what was the equipment that was used to collect this data. But when we plot it, you're going to see it's very, very detailed. Like, it was taking point data, but very, very close to each other for that field. And then it was collecting differences in elevation. So here, the grid code, even though, again, this data came to me this way, so I just want to tell you. So if I send you this data here, especially if it doesn't have, so right now it has a title elevation, so you know at least what to expect it would have. But if it has another name that perhaps is not as informative, and I send this data and I say, hey, here are some spatial layers I have for my field. And then you open this, let's say the name of the file would be like field X. And then you open it and you see this. You'll be like, what is this? Right? Because I mean, grid code, that is really not informative, right? So this grid code column is actually the one that has the elevation in feet. And again, I'm just bringing this point to, you know, to remind you, always try to use concise but informative column names for your future self, but also for anyone that you share data with. So this data here, you know, as is not very clear what it is, but we know, I mean, I know it, I'm telling you, because I was told that grid code here is the elevation column. And then we have the point X and point Y, just the WGS 84 coordinates that were, you know, related to wherever that elevation data was being taken at. Okay, so let's just think a little bit, and I'm going to ask for different people's help here, because at this point we've been doing this more than once, and I do want to start, you know, seeing that you're creating the understanding of what has to be done, right? Because in class, I'm telling you, we're doing on the wrangling, we're doing X, Y, and Z, but when it comes to you and your data sets, each data set is different. So I really want you to think about it as well. So we have to do some wrangling, right? We cannot just simply interpolate this as it is right now. We have to do a handful of things here to get this in a good shape. So let's just come here, get started on this wrangling chunk. We're going to start with a data set that we call 11 on the first chunk. And I will tell you what I want to do first. So the first thing I want to do is just clean names, just to make the column headings all lowercase and standardized. And I'm just going to print it below. So now you see what are the new column names, because they're all lowercase, right? So if I'm telling you that I want to interpolate this, what do we need to do? I mean, we have to do a handful of steps in this wrangling exercise, but some of them, at least, I think you can already think about. So the first question that I would ask myself is, to do interpolation, I have to have this as a vector point file. Is it a vector file, or is it a vector object at this point? No, it's not, right? How do we turn that into a vector object?
Yes, with the code.
STSSF, that's exactly it. So let's add a pipe here. Let's do ST_S_SF. And if you recall, we have to say here the coordinates. So the coordinates would be, so it has an argument called coords, and then we just use the C function and we say what is the name of the columns that have the coordinates. So it's point X and point Y, all lowercase. And I think they have to be within quotation marks as well. So it would be like that, right? So if we do this and we run it, all right, so now we have a geometry column. If we go on the first panel, it is a point vector file, right? However, what do we notice here? That would be the next thing we'll have to do.
CRS is showing NA,
Yeah.
so we need to change that.
Yes, perfect. Sorry, who is that? Is that,
Anis,
okay, awesome. Thanks, Anish. Appreciate your help. That's exactly right. So it has a CRS as NA. If you recall, if we're bringing a CSV file, even though we have the columns that have the coordinates, but the file itself has no extra information to tell R what is the CRS. We kind of have to guess, and a good guess is always WGS84 because again, that's the most common one that is used when this type of data is being collected. But if you recall, also, when we bring in a GeoJSON or perhaps a shapefile, sometimes that CRS information comes with it. So we don't have to set it, we just may need to transform it. CSVs, normally we have to set the original one and then transform to what we want. So if, let's do that step next year. So we're going to use a pipe, and can someone else help me here to remember what is the function that we use to set the CRS?
ST save CRS.
Yes, who was that?
Saker.
Sicker, thanks, Sicker. Yes, that's exactly right. If you remember from our, and this one at least is pretty self-explanatory, I guess, the function name, right? Is it just st set underscore CRS? And then we have to give it a value. If you remember, and we've been using this a lot, we have to first set it to the value that it was collected as, and then we have to change. So this was collected as WGS84. I cannot come here and say set CRS to NAT UTM. That is wrong. We should not do that. We should first set it to the original CRS and then transform to a different one if we want to do that. So the original here being WGS84, the EPSG value for that, which is what we need to put here, is 4326. So we do that. We can run that and then print just to see if our change was incorporated. So yes, it was. I can see there now it says geodetic CRS WGS84. However, we do want to use this and do interpolation with this layer. And as we already talked about, to do distance-based operations like interpolation, we need to have this in meters. Meaning that we have to change now from the original CRS to a metric CRS. What function do we use now? ST transform, yes. So we add a pipe here. Let's do ST underscore transform. It has an argument that is called CRS, and the value, or one of the possible values for the CRS that we need, which is NAD83 UTM zone 16 north, is 6345. Okay, so if we run that and then we print it, we check on our first panel here. Now we see it is a projected CRS that we needed to be S, in the case being a projected in metric system. So there's one more thing, or maybe a couple more things I want to do here that I just want to remind you of. So right now, I mean, if we wanted to proceed from this point on, this is what we needed. This is the bare minimum we needed. I do like to always show you the options. So right now we have, the columns are, this is still called grid code, which bothers me. I don't really like that. I want to change that name. And I also just want to select, I want to change that name. And this is in feet. I want to change that to meters as well, just so we have elevation in meters in case you're presenting something at a conference that requires metric system. And then, I mean, we really do not need the columns object ID or point ID. Those for us are kind of pointless. We could leave them there if we wanted. It's not going to hurt. But I always like to have things tight in a tidy way. So if we don't need them, why do we keep them? I mean, why keep them anyways? So the first thing that I want to do is add a pipe. We're going to transfer or create a new column for elevation in meters. So if you're hearing the word create a new column, think of mutate. I want to call this new column here 11 underscore N for elevation meters. That is, I'm going to provide you the formula. So it's basically we take elevation in feet, and then we multiply that by 0.3048 is a good approximation for us. So just multiplying grid code, which again, grid code is elevation in feet, just multiplying that by 0.3048. So if we run that and we print it, we should have now a new column that is basically a transformation of grid code, which we see right there. And then lastly, just to make things tidier, I want to select only the columns that we need to move forward. And then, yeah, I guess that's going to be it pretty much. So you can add a pipe. We're going to use the function select. And if you recall, we always, for that function, call dplyr : to make sure that select is coming from the dplyr package. And then I want to select the function, the column, sorry, 11_m. So we're going to move forward just with the meter one, comma geometry. So that's all that we're going to use moving forward. If you print that, this is what you would see. Okay. And as always, we're going to do a little bit of EDA, exploratory data analysis, just to first look at some summary tables, see if elevation meters even make sense. You know, if we have an elevation that's a negative value, you know that's not possible. So then we'll probably, that's how we would identify erroneous data that could happen with any data coming in. So let's just run that summary elevation. Again, it's just providing a summary of we have two columns. One is geometry, the other one is numerical elevation. So it's just providing a statistical summary of that. So for this field, for this entire field here, it's given us the minimum elevation is about 45 meters and the maximum is about 54. So a 10-meter gradient. So that would be what, about a 33-foot gradient across this field overall. Okay, so, of course, looking at tables is helpful, but I also want to plot it. So I left you most of the code here. If maybe let's just walk through quickly here what we're doing. So we're starting with elevation W, which is what we created above. We're using a pipe to bring that into a ggplot. Because now elevation W is an SF object, we need geom_SF. So that's what we have there. And if I want to have the different points colored according to the elevation values, that has to go inside AES. If it's not inside AES, it does not work. And then I'm just changing the outline of the points to be 0.01 to be very thin, so it doesn't clutter our view with just like point outlines being black. I'm changing that to scale color varieties C. So C is for continuous. And then I'm choosing the option E, uppercase. So the options are just different color schemes that varieties give you, and they give ranging from the letter A to H, I think. So there's a few ones or a handful of ones there. We could just go ahead and run it just to see what that looks like. So this is our elevation map for this field. And I left you 3 dots there. If you want to come to the scale color varieties and at the end of it add a plus, and you can come here, delete the 3 dots in the comments. And I just did this for us to work together, that I want to specify the theme. So my theme _ map is again that object that we created in the second chunk, where I really specify the theme I wanted my plots to look like. So if you added the plus at the end of the previous line and added my theme map and run it, this is how it looks like. So it's basically, again, just changing the aesthetics of the plot itself, just making it cleaner. Okay, so I have a couple questions here, and maybe different people can help me here. So this is the elevation map. We have darker values being lower elevation, and then so looking at the legend, right? And then yellow, brighter values being higher elevation. So where is, like, if you're just overall looking at this field, where is the gradient? Like from where to where do you see, would you imagine that water would move in this field? Left to right.
From center towards right.
Yes, from left to right, right? So we see higher values being on the western side, on the left, lower values being on the eastern side or the right. That's correct. It's also very interesting that we do see here on this elevation data, we see also those eroded fingers that we already talked about before, right? So we can also see that here. Now I have a question for you, and maybe for someone that hasn't helped me yet. I thought this was a point shape file or a point vector file, but it kind of looks like a continuous layer, right? What's going on? Tyner, do you have any thoughts? It's kind of is a tough one, at least to find visually. Anyone else has any thoughts? Yes, that's exactly it. Yeah, that's it. So it has so many points that looks continuous, right? So we may look at this and think, okay, this is, you know, a shape. I mean, I have the contours, these are polygons, but they're really not. So I just want to show you a quick trick here, just so, I mean, if we wanted to see, we could just print elevation W and you could see that it is a point geometry. So it is point, it has to be point. But why is that looking like that? It's just because it has so many points that it looks continuous. And one way that we could just explore this on a different way is before we send elevation W into ggplot, let's just add another function here. There's a function in the dplyr that's called simple n or simple frac for fraction. I want to do simple fraction, and I basically want to say 0.1. So what this is doing is basically taking a random sample of the entire data set, and it's taking a random sample representing 10% of the entire data set. So if we do that and just add a pipe at the end of that to plug into ggplot and just run it, now we can really see the points, right? So exactly, we had too many points. It seemed like a polygon, but it's actually a point data that we can see now better, I guess. So this sample fraction function, you know, was helpful here just to help identify that there were actually points. If you're doing any random sampling of some sort within a data set, this can help, you know, especially, I mean, if you're doing machine learning, this can be useful for doing different sampling procedures. We're not going to talk much about it, and we're not going to really use this function much more in this course, but I thought it was a nice place to show that as well, and how that can help us to see a fraction of the data. Okay, so we have our point data already here. Even though it's pretty dense, right? So it has lots of points. We still need to interpolate it, because if you zoom in, you would see gaps, but also because we want to interpolate to the same grid cell size that we use for yield. So everything that we interpolate is matching in the cell size and the extent of the field as well. So if you recall, for us to interpolate, we need a grid. For us to create a grid, we need a boundary to start the grid off. So let's bring in the boundary that we use for the yield exercise at this point. If we just add that, the assignment symbol, so that boundary was already a GeoJSON, right? So because of that, we're going to use read_sf to bring that in. And here's something I wanna tell you, especially if you end up working with something that is so complicated, like what we're going through this semester, as far as having so many layers, they all have to be cleaned, processed, interpolated, and so on. The way I'm showing you to do this workflow is to have each one of those bigger topics. So like yield data is its own project, and then we have terrain as a different own project, and then we have EC as going to be a different project, and so on. It means that we could do one of two things. We can either, let's say, oh, I need a boundary here, but the boundary is on a different project. I could either copy and paste that into the code folder here. That is an option. I do not want you to do that. The reason why is if for some reason, at some point, you change that boundary on that folder and you forget to then bring that new boundary over to the other projects that depend on it, then you start creating issues in your code where boundaries are not matching, things are not matching. So instead of copying and pasting the boundary to this project, let's just navigate in our file system through R to get to where that boundary is. So we don't duplicate that boundary, we just use the original one that we had on that project. So if you open and close quotation marks here, // takes me to the main folder of this project. So if you remember, at least on my computer, I have to get outside of this folder to then be able to see the UMonitor folder. So I do another // So in my case, I am now at the main level of my course folder where I see all my projects. In my case, my boundary is in this project called 04 UMonitor. Perhaps yours is as well. So I go in there. Now, if you hit tab, you see code and data and output for that project. So a different project. So we go inside of data folder. And if you hit tab, you should see the boundary.geojson there. Okay, so this is the first time that we're navigating outside of the current project and going into another project to bring in a layer. So we had a few extra or one extra // and then we navigate into a different project. If you successfully got there and you run it, you should be seeing the boundary here. I just want to give a moment here and ask if anyone had issues. If your projects were set up in a different way, maybe you weren't able to follow along. And if that's the case, you got to speak up because we're going to need this boundary moving forward. You don't see it? Okay, let me come around and see if I can. So if you go in data and then hit tab, yeah, the boundary changes. That's it. All right, here in Athens, was everyone else able to do it? No. Online, does someone need help? Was someone not able to do it? All right, I don't hear anything, so I'm gonna take that as everyone was able to import the boundary. So let's continue here. So this boundary, it is a GeoJSON object, it is a GeoJSON file in our file system. So we bring that using readsf because that's the package, that's the function from the package that we use to work with vector data, which GeoJSON is. We bring it in and it is WGS84. So we're going to have to transform that to also UTM. And in a previous class, we did that in two different steps. So we first brought in the boundary and then on a different chunk, we transformed. I just want to do both of those steps here together. If we just add a pipe here, we're going to use st_transform and the CRS number. Let me just get that again. 6345. Yeah, 6345. So then if we run that already and print it, we see that now it is on the projected CRS that we needed. And this is, something also that I just want to mention to you that, of course, in class, when we're going through these, I'm trying to break them down into smaller pieces so we understand what's going on instead of giving you a very long pipe flow that may be difficult to understand what's happening. But here,
objective boundary not found.
Oh, it didn't find yours? Did you run the chunk? Like when you was reading the boundary? No. Oh, it's because you're printing before you bring it in, so it's giving you an issue. Like it's saying, you just have to delete this. Because so if you run this, it prints, but you haven't imported yet. Yeah. So now it's gonna work. Yeah. Yeah, I actually wanna bring that up to share with everyone what's going on. So Dennis was having an issue saying boundary was not found. So what happened on his side is he had the code like this. Where if you do this, and you have not imported your boundary yet, what it does is it first tries to print and you hit play. It first runs this, so it tries to print boundary W, but if you have not imported that yet, it is not there for you to print, right? So he was having an issue that the chunk was stopping here saying, nope, this object doesn't exist. That's because he, only imported it on the, like afterwards. So basically just have to delete that from that point, and then you run it, and then you import, and then you can print it to the console. All right, so we brought in our boundary. Now, the next thing is for us to create our grid, right? We have already also done this before, maybe not as much, so I'm not gonna really ask anyone to help me here, but let's just, so again, this step we've done in the past, we're just gonna be redoing that again. To create our grid, we're gonna use the boundary that we brought in, right? So boundary W. We use a function called st_make_grid. So we're gonna make a grid based on that boundary. And here it has an argument called cell size. I wanna say equals 10. So what is this 10 here? It is 10 meters because the boundary is in meters, right? That's the projection. We add a pipe here as well. And we need to transform this to SF. So we use a function st_s_sf. That's mostly because when we do the st_make grid, it kind of changes a little bit how that object looks like or is interpreted by R. So we just have to bring it back to SF. If we just run it up until this point and we print it, this is still, now it's a grid that the cells are polygons, right? And it's basically, it just has, in this case, like 6,435 cells for this field. If you remember, and again, this is important for you to make this distinction. We're creating the grid as vector, right? So the cells are polygons. They're not pixels. If you think of like an imagery. However, we need the grid to be as raster because that's how the interpolation function accepts the grid as. If we give a vector grid to the interpolation function, it will not work. It needs that to be in raster. So we're going to transform this, what right now currently is an SF object. It is a vector. We're going to transform that to raster. So we can use for interpolation. We do interpolation with the raster, and in the end, we're going to transform again from raster to vector. So we go back from pixel to polygon again, because that gives us a nicer data frame to look at and see all the columns and see exactly where the cells are.
So the features to me looks like the point is a simple picture collection with one picture and the zero field. So you say like 64.
Yeah, so the 64, like 6,435 rows, each row is a cell of the grid.
Yeah, what I'm saying to me is different. Say one feature.
Oh, it only has one? Is that what you're saying? Did you remember to do to transform the CRS to UTM?
Yeah.
So when you print your boundary W, does that say NAD83 as the projected CRS?
Yeah.
And you have your pipes here connecting? Let me come around. So yeah, it's still WGS 84, that's the reason you have to do the state transform up here. Yeah, so if you look, let me show the code, so. Yeah, you're having issues because you're using, you did not change from WGS 84 to UTM, so you still have as a geographic. And if you remember, geographic information or geographic CRS do not work well with distance space functions like interpolation. So this is, yeah, you're just missing that part right there. So if you add that pipe and then change from WGS 84 to UTM, make sure you run that chunk so that change is incorporated. And then that's gonna work in the chunk below. So what happens is if you have it as WGS and you come here on the make grid and you say cell size equals 10, this 10 is interpreted as degree. The reason why you have only one cell is because if you have a cell size of 10 degrees, that is basically the whole field and more than that. So that's why I just have one cell. And again, stressing the need to transform that to UTM in meters. All right. So let's continue here as we were talking about. So now we have a grid where the cells are polygons, right? So they're in a vector shape. For us to transform that to raster, we add a pipe, hit return. There's a function called st_rasterize coming from the stars package. Remember the stars is a package used for raster data. And then it has a couple of arguments here, whereas dx and dy, which is like the distance of the cells. So we just want to keep that the same. So dx equals 10, dy equals 10 as well. So if we do this, we did this exercise in the previous class. I'm not going to do it again because it is the same grid as we did before. But we do have like this grid here is basically takes the field. It makes like an imaginary box all around the field, touching the outermost points in all directions of the field and calls that the bounding box, meaning that right now our grid is both inside but also outside the field. If you remembered, for us to not interpolate outside of the field, because that makes no sense, we have to crop this raster to the field boundary. So you do a pipe, there's a function called stCrop that we just give here the boundary. So imagine the boundary now being the cookie cutter that we're going to basically like cut that raster that right now is all around the bounding box, which includes parts outside the field. Boundary W, not M. Okay, so let's if we just print it here and we go so now it is a stars object, which represents raster data. So the way that it looks to us is a little bit different. Like we don't really see the data columns as we do with the SF object, but it does gives us like a summary of whatever it has. So right now it only has an ID column, which is the ID of each one of the pixels. That basically just goes from 1 to 6,000 and some whatever the number of rows this has. That it's not a very informative statistical summary to look at. But just one thing to notice is now that we have NAs, which we did not have before, and that's again because we just cropped to the field boundary. And remember that a raster is a continuous layer. So if you crop it to something, it's not like you're removing the pixels outside of the field boundary, you're just setting them to NA. So they're still there, but they're coded as an A instead. Okay, so let's just do a quick plot here. I left you the beginning of it, so the ggplot is there. Let's just add a plus. And so I want to plot this grid R, which again is a stars object. So now we use geom_stars, not geom_sf. geom_sf is for SF objects. Just want to say data equals grid R, which is the object that we just created. Just add a plus and bring in our theme that we created in the beginning. That's called mytheme_map. That's all. So if we just plot that, a couple of things again to notice is right now it's coloring the points by ID, which is not very useful for us because it's just ID of the cell. Right, so it's just going from 1 to 6,000 or something. And then everywhere else that we cropped with the boundary, outside of the boundary now is set to an A. So that's why we see them grayed out, but it's still there, right? Still there. And also we talked about this in the previous class as well, but for some reason that I don't know the explanation for. So stars package, SF package, one build, so stars for raster, SF for vector, they're built by the same person. And for some reason, when this person was designing the geom stars function, when we use that function, it doesn't make the plot, the range of the axis to be as a map would be. However, when we use geom SF, it does. So just, that's why this field looks a little bit off the way it is just because the axes are not set up on a map way. That's not a problem, it's just a visualization component. You know what, I think that here is probably a good stopping point before we do the interpolation. So let's stop here, and I want to create the GitHub attendance for you to respond. And then it's February 4th. So if you are watching live, go ahead and claim your attendance. And remember that every time that I open the GitHub issue for attendance in class, I do not accept answers outside of class. So make sure you claim while I was still in class. And anyone has any questions or comments of things that we did today? All right, I don't hear anything. So basically today we talked about interpolation, we brought in the boundary, we brought in the elevation data, we wrangled the elevation data, we used the boundary to create the grid. And now the next step that we're going to do on Monday is going to be to interpolate that elevation data to that grid, and then use that interpolated elevation data to create secondary terrain variables that then we'll export and use them later in a different exercise. If no one has any questions, then that's all for today. Thanks everyone, and see you Monday.